Hello everybody, it is me, Steve. It is January 9th, 2018 as I make this video. And this one is going to be a two-parter. It's going to be lunar observations and hemispheres and wobble. Now, I'm going to talk about first how we observe the relative position of the moon in the sky as if we're in the northern hemisphere or versus the southern hemisphere. I haven't seen a lot of videos made on this, and the explanation is actually really simple, so I thought I would make one. And the second part is going to be the wobble part, is going to be about the oscillations and wobbles that we observe throughout the lunar cycle, referred to as lunar liberation. No, it's not a SJW term. But anyway, so first I'm going to start here. This is just my title card. The moon and the earth are to relative scale here. Obviously, they're not this close to each other, but their sizes are correct. However, my model is not going to be to scale. And I will get into the reason for that for a moment. But first, I want to show you an actual to-scale representation of the earth and the moon system. All right. First of all, here's the ecliptic. That's the plane of the orbit that Earth is on as it orbits the sun. All right. This is the lunar plane of orbit. All right. It is inclined. It is inclined 5.15 degrees. It is not with the ecliptic. And this is the reason why we don't get solar eclipses all the time or lunar eclipses all the time. But as you can see here, the Earth is to scale with the moon here at its actual distance at this scale. Now, if I built my model like this, you're not going to see this. All right? You're not going to see what I'm trying to illustrate. So I'm going to have to bring everything in. But also what is on here is Earth's axial tilt and the lunar axial tilt. Now, the lunar axial tilt from the moon's orbital plane is 6.68 degrees. But relative to the ecliptic, it's only 1.53 degrees. All right, so I just wanted to show you that and show you why my model is not going to be to scale. Now, first we're going to take 2 points on the Earth. I just picked two random places. Latitude is more important than longitude here. Marionette, Michigan in the USA, Upper Peninsula. First point because it's really close to 45 degrees north latitude. And then I picked Queenstown, New Zealand, because it is really close to 45 degrees south latitude. And this is going to be the two models Earth models I'm going to use along with the moon to show you why people in different hemispheres on the same night, observing at the same time, will see the moon look rotated from each other's vantage points. All right. Now here's the model. First I'm going to explain the model a little bit. This is for the northern hemisphere. All right. What you see here, the Earth and moon, is not to scale. None of this is to scale other than the angles, because that's all that's relevant. Me trying to explain this. All right. The Earth, obviously the western hemisphere, is facing you. In order to observe this, the western hemisphere would either have to be turned the other way with the moon behind it, or facing this way with the moon in front, and it would be nighttime. But if I try to do that, you are not going to see what I'm trying to illustrate. I hope you can picture this in 3 dimensions in your mind. If you can't, I'm sorry, I can't help you. That's you, not me. But it's not necessary. Even if you can't, you should still be able to get the gist of this. All right. Now, what you'll see here is you'll see this line. This line represents the ground surface at my location at 45 degrees north. All right. So I just extended the line out so I could get an angle. This line would be as if I was looking at the moon. And we're just going to assume the moon has no axial tilt and that it's in the ecliptic or at a node, although it wouldn't be in this situation most likely. All right. The green ground in the upper right here. All right. That is just me taking that initial plane from your observation from the Earth and moving it to the moon to show you that's ground level. All right. Now, if we take this and rotate it so the ground is flat as it would be as if we were standing upon it, we would notice there's a minus 45 degree tilt, or a 45 degree tilt to the left from the moon's north. And I could have used positive numbers here, but then I would have had to use negative on the other one, and it just didn't make any sense. So I just said the rotation to the left is minus 45 because I got to get into some math in a little bit. All right, so that's the northern hemisphere. This is the southern hemispheres if you were watching from Queenstown, New Zealand. And it's very similar. It is also at 45 degrees, but it's south latitude. So what I did here was I flipped north on Earth and the moon, just so we could orient and keep our angles looking the same in the two diagrams on the top. All right. So we extend our plane from the planet as if we were standing on the ground, just like we did in the first one. And the line to the moon, which would be your vantage point, and in the upper right, I just moved the ground to the right and made it green. And using that on the bottom, we did the same thing we did before. We rotate the ground and we get our angle relative to north. Now see, this time it's gone the other way, so we have a positive number. And if you measure that, you get 135 degrees in this angle. All right. So what does this mean? All right. Well, this is why we see two different relative rotations, if you will, of the moon from two observers on two opposite sides of the planet at 90 degree difference in latitude, or actually, 90 degree difference in latitude from one another. And this would only work if the Earth was a sphere, and it does. And I did a video, which I'll link below, showing my observations compared to somebody in Australia's, although we were a day apart. But you can compensate for that. Just watch the video below if you want. All right, so now we have our Marinette, Michigan, USA, and Queenstown, New Zealand. I took both those slides and just put them on one for you. And so what do? Well, we subtract the 45 degrees that we saw in the northern hemisphere from the 135 degrees we saw in the southern hemisphere. We get 90 degrees. So that 90 degrees is our latitude difference from one another as well. And that's what we should observe if we have two different observers at two different latitudes on the planet. And we're actually going to try, I'm working with Lanny right now, I'll link to his channel below as well. He's going to try to take pictures of the moon during our ISS transit attempt on the 27th. He is slightly north more in latitude than me, not by much, but 6 degrees or 7 degrees, I think. So, but that should be enough for us to see the relative difference in how the moon looks oriented from one another. I'm trying to get somebody to do it south more, like in Florida or Southern California as well, so we can get a better angle. But like I said, I've already done this, and this works out. And like I said, this only happens on a globe. This would not happen if the Earth was not a sphere. And so, this is part 2. All right, so here we go. Is it true that we only see one side of the moon? Yes and no. The moon is tidally locked from to the Earth, meaning one lunar day is equal to one lunar orbit around the Earth. This does not mean we only see 50% of the lunar surface. This is why I'm saying yes or no. It's coming up here. This is where I'm going to start talking about lunar liberation. All right, and I touched on this on a previous video of mine, which will also be linked below. I just didn't call it lunar liberation because I just didn't want to get into it in that video. We can actually see 59% of the lunar surface over time due to lunar liberation. There is latitudinal and longitudinal apparent wobbling of the moon as seen from the Earth. This allows us to see more than 50% of the lunar surface and makes the moon appear to oscillate or wobble from night to night. Now, this isn't the same thing as being able to see it in two different hemispheres. All right, that's perspective because you're two different locations on the Earth. This is from night to night and through its orbit. All right, there's also diurnal or daily liberation. It's a parallax effect. This is a small daily oscillation due to the Earth's rotation. It can be seen change from moonrise to moonset. It's greatest at the equator at about 1.03 degrees and diminishes as you approach the poles, which is exactly what you'd expect to see on a globe if the Earth is a globe, all right? And I will eventually do a video showing the daily libration, but that's in the future. That's not going to be right now. It may even be next month. I may even wait for it to warm up a bit because I'm already tired of getting cold. So that's all I'm going to say about daily liberation right now, and I'm not even going to get into it here. All right, but here is just some photos showing you how liberation is. All right, remember in my last video about the moon, I forgot what where the green arrows are pointing to Tycho crater. I forgot the name of it. I just had a massive brain fart. It's like the most obvious feature on the moon too that everyone knows. But here are the sources on the right, and now on the bottom I put a red line. I put a red line on the left about where you can see the edge of the moon. Now I moved that line to the picture on the right in the 2A, and now you can see more of the moon. Well, what does this? All right, this is that liberation. All right. Now, the liberation, because of the moon's orbit and because of your vantage point, changes from night to night and lunar cycle to lunar cycle. And NASA has great videos showing this. And I already linked in one of my previous videos to one, and I'll link to another one in this video as well. All right, so here we have phases of the moon over a 2-year period. Here's a source. We got that out of the way. All right, now I'm going to talk about it. Oh, just for future reference to anyone taking photos of every full moon cycle in a year, we almost never get 12. It's 13. 365 divided by 28, which is about a lunar cycle, gives you 13 and like a day or something. So we actually get about 13 full moons a year, not 12. So just remember that. But what is this? See these red dots I put all over this? All right, this is somebody's over a 2-year period. They took pictures of the full moon, and the red dots are on Tycho crater, just like the 2 slides before. And what they show is, if you look from slide to slide, what you see is it's not in the same position. This is how we see more of the moon than just one side facing us. That tidal lock does not mean we only see 50% of the moon. All right, sorry, those cats in the background being really loud and fighting and playing right now. So yeah, that's that. But anyway, all right, so as you can see with the red dots here, it changes. And look at the moons look different in size. That has to do with perigee and apogee. Here's the next slide. All right, so what I did here is I took the full moon at perigee. Perigee is when a celestial object is closest to us. Apogee is when it's at its furthest. So if it's closer to us, it's going to look bigger. If it's further away, it's going to look smaller. All right, this is the whole supermoon thing versus micromoon. The supermoon looks about 14% larger in the sky to us than does a micromoon. All right, and as you can see, I did green circles. The full moon is at perigee for the full supermoon, red for when it's at apogee or micromoon, and the yellow circle just shows you the full moon as it's seen, from its average distance or semi-major axis. And all those circles are based on the size of the supermoon or the green one. They're all the same, just to show you. Now, are these moons to scale in this photo? Obviously, there aren't, 24 moons side by side. They're just the different phases, or just the different full moons throughout the calendar years. So, but are they to scale in this picture? Well, I just wanted to test it just to make sure it was, and as it turns out, they are. So here's our green circle taken from the previous diagram, our perigee with the diameter, which was 2.14 inches on the program I was using. Well, to figure out the area of a circle, you need the radius, so you half that. The red circle here is the apogee with its diameter. I shrunk it down to physically measure it at the apogee, one that I used in the previous photo, and luckily I got a radius of 1, diameter of 2. All right, we can drop the units after this point because they're not relevant, because I'm trying to get a percent, just to simplify things. So then all I do is plug these values into the area of a circle, and on the lower left here you see the equations, and R1 is my perigee, R2 is my apogee. And now, well, we need to calculate the percent increase in size. So we take those two values, that 3.6, and divide it by that 3.14. We subtract 1 from that number because we're going to get a number above 100. All right. Then we multiply that by 100 to get our percent. And from my physically measured percent on that slide, I got 14.6%. So 14.6 is close to the 14% observed. So the previous slide is essentially to scale. So it's a good, accurate representation of what you would see throughout a 2-year period on full moon cycles. This last slide, all this is the data I got from NASA's website. They're on one of their fact sheets. It's in the lower right. And I just copied and pasted it from that. So sorry, computer beeps at me because apparently its updates are far more important than anything I'm actually working on. Apologize for that. So here's just some information I took directly from that web page. You can go there. There's all kinds of basic astronomical data NASA has. But anyway, that is it. I hope you learned something. Feel free to leave comments below. And thanks for watching.